So thank you all for coming. For those I haven't met before, my name is Andrew Case, and I spend a lot of time doing memory forensics and malware analysis. Today I'm going to be talking about one of the latest research efforts I was involved in, which is we did an exhaustive study of all of the Windows rootkits that were found in the wild in the last couple of years. So ones that affect Windows 10 and all of the security protections are enabled, they can load also. Because we deal with these types of threats a lot. Obviously, rootkits in general are a grave threat to privacy and security. Once a rootkit's on a system and active, they can do whatever they want to the machine. They have full control over all the operations. They can blind any security products looking for any activity on the system. And we noticed in our investigations, I would say over the last 2-3 years, and this was shown by other security vendors as well, because we read all the reports that come out, that there really was a return to rootkits appearing on Windows. When Windows 10 first came out, Microsoft had driver signing enforcement. If you're not familiar with that, we're going to have a couple slides that explains it in great detail. But the idea is Microsoft came up with this driver signing enforcement idea, and it made it where you really had to be a legitimate software company, work with Microsoft to get your driver to load into the kernel. Obviously, something fell apart with that protection. It fell behind the times because we started seeing rootkits on Windows 10, which is not something we were used to. So again, we wanted to deep dive these rootkits, figure out how were they actually loading on the machine, what were they able to do on Windows 10 that they couldn't do on Windows 7 and before, and obviously how could we detect them. Before we start any research project, we always come up with a goals list so we don't get lost and fall down rabbit holes. I'm sure no one here has done that before. So what we wanted to do was come up with triage techniques to figure out, does a machine have a rootkit on it? And then if we have a bunch of machines that we're supposed to protect or sweep across, how do we figure out quickly if a bunch of machines have signs of a rootkit? So we wanted to make these effective. We wanted our techniques to not miss rootkits that were there, but we also didn't want a billion false positives. Saying that every machine and environment has a rootkit when maybe 1 or 0 of them do is not very helpful. And then we also wanted what we researched to be scalable, because it's very rare that we deal with like 1 or 10 machines in investigations. It's usually a lot of them that we have to get through quickly. So if you've seen my talks before or research out of our group, you know the 2 places we like to look are memory. So we'll see some memory forensics. This is where malware can live undetected, where it also has full control of the machine. And when it comes to historical records and being able to sweep across an enterprise very quickly, event logs really can't be beaten. So we'll look at that as well. If you're not familiar with memory forensics, this is where you get a capture of RAM from a system. So if it's a laptop with 16 gigs of RAM, you're going to walk up to that machine, run your software, maybe you push the software across the network, and then you walk away with roughly a 16 gig file. Obviously, in an enterprise environment, you want to do it a little better than that. But the idea is you're getting back a static copy of what was in RAM at one point in time. The reason memory forensics is so powerful, and the reason why it's used so much, is that all of the malware that was present on the machine is going to be stuck in memory along with its exact configuration. So especially when we're talking about kernel rootkits, those things can be really nasty. Even if you're great at reversing, even if you have years and years of experience with it, it's really annoying to deal with kernel rootkits if they're doing anti-forensics techniques and so on. Whereas when you have a memory sample, the rootkit has already put itself into memory. It's unpacked all its components, decrypted everything, and makes your life a lot easier. And then the other reason why memory forensics is so important is that malware of this type is truly hidden from the live machine. So whether it's your favorite tool, something out of like sysinternals, other software that you've written, if you're reliant on the live APIs or on the live system to tell you what's going on, that's precisely what the malware is going to hide. So you're never going to see it anyway. And this was just an interesting report from Microsoft that I clipped into the slides where they talked about this core lump software. This was actually an awesome report. They basically burned a company in Australia that was like for hire, kind of like cyber mercenary groups, if you want to call them that. And Microsoft just burned their entire toolkit down to the ground. And this was from it. So Microsoft called the malware, or one of the main malware component, core lump. And it talks about how it lives only in memory. And this is just one of many examples of, if you're not doing memory forensics, you're going to miss the malware on that machine. So we'll see a lot of that. The other thing that's incredibly powerful are the event logs. If you're not familiar with event logs, these will record a wide range of activity that happens on the system. This occurs even by default, but then if you configure them a little better, you get even more information. And the other great thing about event logs is they're timestamped down to the second. So if you see that something happened on the machine that you care about, now you know the exact second where that happened. And in many organizations, almost every organization that we work with now, the event logs are centralized in some sort of way. So you can say, from one system, write your query. You want to know, do certain event IDs exist? Do certain event log sources have records that you want to look at? You'll see a few examples of that in the slides. And that immediately tells you if there's somewhere to dig into. And so it could be an enterprise with thousands and thousands of machines. And like we'll discuss in the slides, there's some event IDs that are never good. And if they're on any of the machines, you immediately need to get memory, get your files off of there, and start a real incident response process. So between memory forensics and event logs, if you're doing malware analysis, IR, these are by far the best places to look. So now we'll discuss how do rootkits actually load on a system the recommended way. If you've done malware analysis a long time, back in the XP days, I know there's some like hacky ways that drivers could load. Microsoft has closed those out. So I really just want to focus on the Windows 10 ones, the ones that you're going to see most often in the wild. So the way you load a driver the recommended way is you're going to create a service. Services are very powerful components of the system. You can have services run as a DLL or a process, and it's also the way to load code into the kernel. When you create that service, you tell Windows where the path is to your driver file, so that executable on disk for your driver. And then whenever you tell Windows you want it to load, upon system boot, after a certain time frame, whatever that trigger is, that's going to get that loaded into the kernel. So for rootkits that want to load, they normally want to load at startup. They want to maintain persistence on the machine. They're going to create a service. Now, there are event logs for this, but it's really noisy because every third-party application, lots of random drivers are going to create services and so on. So I'm aware that services create event log records, but we're not going to talk about those because in a real enterprise, you can't triage with them. So you might be wondering, though, I kind of mentioned it before, sure, rootkits can tell the operating system that they want to load their driver, but as I mentioned, Microsoft made a bunch of changes in Windows 10 so that unsigned drivers, so unknown, non-secure drivers, aren't supposed to be able to load. This talk I'm giving today should not exist if this worked. Obviously it didn't, so I'm here talking about the rootkits that are in the kernel. So the idea here is if you want to get a properly signed driver on Windows 10, so we're talking about legitimate vendors here, not rootkit authors. Say you're an NVIDIA or anyone else that has a driver for something that you ship to your customers, you have to cross-sign that driver with Microsoft. So that means you have to upload a copy of that driver to Microsoft. You imagine rootkit authors don't want to do that. It's like sending it to VirusTotal, kind of defeats the purpose. And then at that point, Microsoft cross-signs your driver. So this is really bad for you, right? Because Microsoft has a copy of the file. And then to get one of the certificates that you need to do this cross-signing, you don't just go to like GoDaddy or something like the old days and get one. There's verification of the people involved, the company involved, and so on. You can't just get like an anonymous email address and 5 minutes later you have your certificate. The motivation for having this cross-signing and this really difficult or kind of I'm going to call it difficult way of getting your driver cross-signed is because we all know of the famous stories of when this didn't happen, where you could take any code signing certificate from any company, sign your malware with it, and load it. The very famous example of it was Stuxnet. There's been a bunch of other ones where companies get hacked. The attackers purposely target their code signing certificates. Can you imagine if every laptop, desktop in your environment had an NVIDIA card, and then you had to disable all of their certificates, and now no one has a screen they can look at anymore? Like, it's just not feasible. So this is a very, honestly, it's a really effective way by the attackers steal the certificates. Now they look like legitimate software. A lot of AVs and other EDR type software are going to skip scanning your file or skip scanning it as hard. And so this works really well, which is why we now have the cross-signing. And as I mentioned before, there's a lot of steps to do this. If you want a lot of pain, you can go back and read these slides, but it's not a 5-minute thing to get it cross-signed. So at this point, you're thinking, okay, there really shouldn't be rootkits on Windows 10. They shouldn't be able to get in the kernel unless somehow they make a fake company with fake identities and all this craziness. Well, what malware authors did is they just said, I'm just going to break the driver signing enforcement protection. Now it's like we're back on Windows XP days, and I'm just going to load whatever I want, which is obviously not good from a security perspective. So this is known as bring your own vulnerable driver. I'm going to spend a couple slides on it. There is a talk at 2 in this room, in this track right after lunch, where the whole talk is on vulnerable drivers. I didn't know that obviously a few months ago when I submitted my talk. But if you've never heard of this before, if you want a lot of technical details, I would recommend coming back to this room after lunch for that talk. But the idea with bring your own vulnerable drivers is you're going to take a vulnerable driver that is signed, so this is from a legitimate company. You find a vulnerability in their driver that allows you to manipulate code in the kernel. And this has been used by dozens of APT groups in all sorts of attacks. All the rootkits that we see load have to do something with this if they want their driver to load. Because again, their unsigned rootkit's not going to load if the DSE is still on. So they're going to use a vulnerable driver, use that to manipulate the kernel, and then from there they'll be able to load their code. This is one of the first really good public documentation of this, like exhaustive documentation of this. This was from Rapid7, I believe, a year ago. There was actually a blog post by Splunk last week where they went back through it all and all the drivers again, because this just keeps getting used over and over. And the idea is you might recognize some of these driver names. So like VBox is VirtualBox. There's some for like Procmon's one of them, part of sysinternals. So there's a number of drivers. These are cross-signed by Microsoft. And again, the idea is they're vulnerable in some way. Maybe they have bad API design so that any process can send them commands. Those commands will let you write to physical memory, read physical memory, overwrite the kernel, and so on. So you have literally dozens of drivers that you can use to still manipulate the kernel and then get it to where you can load in your malicious rootkit. And the problem with this, you might just think, okay, there's vulnerabilities in software every day. There was just a talk right before this on that. And these are not all ones that can be fixed right away. They're not all buffer overflows. They're not all things like that where you just update the code, recompile it, and now they're not exploitable. Like I said, a lot of these are by design. So you would have to go to the company and say, hey, your driver is being abused by rootkits. Redesign your software stack from scratch in a week so we can stop this, and then ship it back out. That's just not going to happen. All those companies aren't going to fix it. And the other problem is there's legacy hardware, right? Like there's a certain, I'm not going to call them out, but there's a certain hardware vendor that sells network cards to a lot of enterprises, and their drivers are notorious for being vulnerable to this attack. But it's the same thing. If Microsoft pushed out and tried to disable all those drivers at once, now those machines can't get on the network, they can't send packets, it's not going to work. So there needs to be something done about this, maybe some fall off period where those drivers could be disabled. But until that happens, rootkits are going to keep loading through this way. So once you've found a vulnerable driver, what can you do with it? As I said, you can manipulate the kernel at will. You're going to eventually get read-write access to the kernel, but it's very hard to do really intense, detailed operations through that primitive. You're basically trying to write a rootkit as shellcode, which that's very hard. That sounds absolutely terrible. So instead, what rootkits are going to do is they will simply, the second step here, they're going to disable driver signing enforcement. Now they can load whatever rootkit they want, and they can just create a service, or they can load it from a pre-existing service. The rootkit is active, and all of these defenses fell apart. So again, if driver signing enforcement was a little more robust, if these issues didn't happen, this talk wouldn't exist. We still wouldn't have rootkits on Windows 10, but we do. And so until everything is fixed that I mentioned on the last couple slides, this is going to keep being a problem. We see it all the time. And like I said, there's vendors, at least every couple weeks, there's another blog post from a big vendor talking about it. So how do rootkits actually disable driver signing enforcement? There was an old way for it. So starting in Windows 8.1 plus, so no one used that anyway, so we call it Windows 10. The idea was inside of the kernel, there was a global variable called G_CI options, and it was just a basic integer or number. If it's 0, it's disabled, and if it's 1, it's enabled. Very simple, right? So with that basic primitive you got from having a vulnerable driver, you just had to locate that variable in memory, switch it from 1 to 0, and then you could do whatever you want. Obviously, that's kind of ridiculous for all of the infrastructure where you have to upload drivers and such. So Microsoft wanted to fix that. We'll get to that in a couple slides. But my first thought was, well, we should be able to detect that with memory forensics, right? We can find that variable ourselves. We can check it. And if it's on a Windows 10 machine and that variable is set to 0, hey, there's a rootkit that switched it off, so we need to look into this. Unfortunately, that didn't work. I probably should have reversed those rootkits a little more before writing the plugin. The plugin was kind of short anyway. but I eventually realized that all the rootkits reset that value after. So you can imagine the machine's clean, the attackers get on the system, they load their piece that's going to disable this, so they set the value to 0. They then load their malicious rootkit, and they set the value back to 1. So the enforcement was disabled for a small enough time period to let that rootkit load, but then it goes back to how it was previously. So then I kind of re-examined it. I'm like, what can we do in memory to find this anyway? I found these 2 really awesome blog posts. So the GCI options in a virtualized world and the Swan song for DSE tampering. 2 separate blog posts. If you're interested in this, I definitely recommend looking that up. And the long story short is there's no memory forensics way that I could figure out to definitively know if DSE has been tampered with, because these list out like 20 different things. If you reverse the code path, there's a ton of functions called, a ton of variables consulted. So there's at least a couple dozen ways you could disable DSE, and it would be very hard to have like a comprehensive volatility plugin that did all of those. So it was back to the drawing board. Memory forensics wasn't going to immediately tell us if this happened. But luckily, Microsoft now has what's called, in their expanded event log set, they have 2 things that are really helpful to us. One are the code integrity logs, and as we'll see on the next slide, the security mitigation logs. Again, this is event logs. This is just in the tool I use for event log forensics. It'll look exactly the same in anywhere else you ship your event logs. And the idea is inside of the code integrity provider, there's an event ID 3004. It's kind of funny. It says the first sentence is like, this event isn't common. So I'm glad that like rootkits loading on the machine isn't common. But the idea is this is going to fire whenever an unsigned driver loads into the machine. And if you read the whole page, I have the references on my last slide. If you read the whole page here, there's some other closely related numbers. So you want like 3005 and 6 and so on. But the idea is Windows is like, hey, this unsigned rootkit was trying to load for some reason. That shouldn't happen. I'm going to throw that in the event log so you can find it 3 months after you've been attacked, but the rootkit's going to load anyway. Like, come on. The good thing about this is, remember, event logs are timestamped. So you at least know the second of when your machine had a rootkit active on it. Again, this is probably going to be loading in a service, so this would be every time the machine rebooted, it would come back. But you can get back to that first time pretty easily of when did this show up on my machine. And this would be a really good example. On Monday, when you're at your office, if you sweep your network for the code integrity provider, event ID 3004, and you see a bunch of hits, it should be rootkits. I'm going to get to an exception in a second. I took out the slides. I didn't think it was very fun or nice, but there's this one, which you'll definitely want to check. And then as I mentioned before, normally rootkits are going to have a service associated with them. It's 100% possible, and it happens where a rootkit will load its service as just the driver, and then you have this nice driver file sitting on disk. That's what you're seeing on the previous slide. Another variation is they'll have a process-based service as well. That process might load the driver part, or it might just be a separate component, so now you have the malware active in userland and the kernel. So on this machine, where this is a real rootkit, we'll see some output from it when we're running volatility plugins. The previous slide was the kernel driver component loading. And this slide, which you can see now we're in a different provider. We're in the security mitigations part. The event ID is 11. And it's telling us that a service host process, which is like a privileged service, loaded this unsigned DLL. So again, you're like, why do you allow that to happen? You're writing out an event log, just block the DLL from loading in the first place. But by querying for these IDs, you have a really good idea of which unsigned drivers loaded in the kernel. And this one's not documented extremely well. The other one really isn't either. But the idea, what I gather from it, is when an unsigned DLL loads into a privileged process, like a service host or something else, it's going to flag this. If you have some random third-party application that's loading unsigned DLLs, it's not going to trigger here. But your main It's really important here because this tells you which services are loaded and created on the machine with unsigned executables, which is a really common way that rootkits operate. Now, the exception to this, and it gave me a heart attack for a second, is when I originally found all this out and was documenting the IDs, I like to go look across the sources I can see from historical investigations we've done, and then some live data on client networks, because I want to know, like, is this just going to produce a billion false positives, and it's a waste of time. So the first thing I did was look for this one, and I got thousands of hits. And I was like, there's no way that... So at first I thought my query was wrong, like I typoed something. I'm like, no, right provider, right ID. Again, thousands and thousands of hits across like every customer that we have. And I'm like, there's no way that like all this was missed and like there's all these rootkits and everything. There's gotta be something wrong. So I'll talk a little slow so you can try to think on it. But if you can imagine, there's one class of software products that make a lot of claims that are usually wrong, and they usually end up shooting themselves in the foot to supposedly provide security on your machine. That's what those thousands of hits were. Now, there was definitely signs of malware that I found in those queries. I checked with our services team. They had known about them, like there was previous, IR situations for them. But outside of those, the tens of thousands of hits, every single one was an EDR vendor. Unsigned DLLs, their services loading, they weren't not the driver ones, but these DLLs from disk loading into services, every one was a security product. And if that doesn't scare you, what that means is those vendors are shipping DLLs that aren't signed and then loading them into service host processes that run with the most privileges possible. Now, if I was a red teamer and I did offensive research instead of talking about stuff like this, I would profile every EDR vendor there was. I would find ways to infect those files, or you could really just replace those files if you wanted. And now you're going to load into those EDR products. You can disable everything, and you have a really nice persistence mechanism, because what's the first thing everyone does is they go into their allow list and they put everything related to their EDR product. Well, at that point, you just put into your allow list everything that the malware does. So I very easily think you could get at least one, if not two, black hat talks out of that. Just throwing it out there for someone who wanted to do it. But with my position, I don't think that would be a very nice thing to do. But it would definitely work. Like, it just blew my mind that run-of-the-mill, like every single one. Like, if you were at RSA last week, it would be just like looking at those logs, all the vendors that load unsigned stuff on your machine. So at this point, we know that rootkits can load into the system. We know they're not supposed to, but DSC can be bypassed, as we saw and as we talked about. So the other thing that we wanted to research as part of this is the kernel patch protection, normally known as PatchGuard, kind of the same idea. So the idea is there was rootkits since the earliest days of Windows, and they kept abusing the same features over and over again. So Microsoft had a really good idea, which is, why don't we protect those features, and so the rootkits don't have that level of control over the system. So for a lot of the old things that rootkits did, if they try to do them now, the machine's going to blue screen, which is not very helpful. Also, if you have full crash dumps enabled, that's going to trap the malware into a memory sample. Now, I put stars, because there's always someone who likes to raise their hand and say, well, technically, the malware can do this and get out of it. I know, I'm well aware of that. But in 99% of the cases, the malware will be in that crash dump that is produced, and the thing that caused the blue screen will be the malware itself, which is not what the malware authors want to happen in the wild. So rootkit authors want to avoid PatchGuard, and then you also have to think to yourself, like PatchGuard really doesn't have a lot of bypasses. They're patched very quickly when they do happen. So looking at the places that PatchGuard protects is not very good for triage, because 99.9% of the time the malware is not going to be there because it would have crashed the system out anyway. So I wanted to figure out what was the latest version of what was being protected by PatchGuard, and sometimes Twitter is actually cool. Like, I tweeted it out. Like 30 seconds later, one of the gods of Windows internals is like, hey, run this in WinDebug, and I've solved it for you. I'm like, this is awesome. So took that WinDebug command, loaded a VM, ran it through WinDebug once it was loaded. The idea here is we're looking for reasons that would cause this 109 exception, which is critical structure corruption. And if you're familiar with memory forensics, or you used Volatility before or anything like that, everything in red literally maps directly to a Volatility plugin, because these are things we wanted to look for in the past to see if rootkits were performing these actions to detect them, and now we don't have to anymore. Some of these, obviously, they're one sentence, and you can make kind of a guess at what they are, and I'm pretty sure some of these are covered by Volatility, but I only highlighted the ones where there's literally, there's a plugin called IDT, where you check the IDT and the GDT, and you can check if the process list is corrupted and so on. So you can imagine Microsoft had similar motivations to we did with Volatility. Like, rootkits are doing something, we want to catch them. Rootkits are doing something, Microsoft wants to stop them from doing it. So a big part of our research effort was to figure out, as we're analyzing these rootkits, what can they do on Windows 10 that is still deadly to a machine? Still going to let them hide from all of your security products, still going to let them steal everything off the system. And so that's what we're going to look at for a few slides. Just a quick recap, when a kernel driver loads, there's two data structures that are going to be created and that we can start our attempt to find the malware or the rootkit. The first thing that happens is a kernel module data structure in memory gets created. You can see that here it's going to have the path out to disk, but just running this plugin is definitely not good for triage because I cut something like 250 rows out of this slide. There's a lot of kernel modules on a clean system. The important part here, though, is the base. So this tells us where that executable is going to be in memory, and then depending what you're doing, the size can be important as well. Besides the module data structure, there will usually also be driver objects. So this is what's going to allow a module or a module to be mapped back to its service. And also this driver here is how processes can talk to it. So a simple example would be if you have like an NVIDIA card, you have that GUI that lets you set the fan speed and the colors and whatever. That is in many cases just going to talk to the device that that driver makes so you can set the values. So when we're looking for these kernel mode components, there's two things we want to look at to start, the modules and the drivers. Again, this would be the place in the registry where that service is. You get the start and the size, and then you get something close to a name. But again, you can't look at this on your own because there's going to be a couple hundred rows there. There's going to be a couple hundred rows, so even on one machine, it's too much to look at on your own. That was interesting and blinding. Okay, so just like... So what we want to be able to do is figure out when rootkits tamper with these data structures. There are APIs on the live machine that are available to you if you're using certain like forensics tools on the live machine or certain malware analysis tools that even from user land can recover the modules and the drivers that are loaded. And then certainly your EDR type products that are loaded in the kernel can figure those lists out the same way Volatility does. So what malware will do is a couple things. One is they're going to unlink themselves from the module list, so they just won't show up on this slide anyway. Technically, PatchGuard protects this, but I've, like, with my own eyes, seen machines where the module's unlinked and it didn't blue screen, so I don't know if that's some, like, bleeding edge feature that I just haven't triggered yet or something. So that's why I have the star there, but this definitely works. The other thing that rootkits will do is change the driver's metadata, which the idea here is they don't want you to be able to know where it is in memory. So if we go back to the driver scan output, this is the base address of where that executable starts in memory. We get another copy of that same data in the module structure. So what rootkits will do is zero that data. That's usually what they do, right? They could technically put something else, but normally they make the base address 0 and the size 0. So now to start, you don't know where that is in memory. So that makes it difficult to find it because it's not going to show up in your normal listing tools. But this is very nice from a memory forensics perspective because now there's this weird disconnect where you have a driver in memory that like technically doesn't exist anywhere and you have a module that doesn't exist. So we have a plugin called driver module. And what driver module does is it compares the metadata from the modules plugin that we saw before and the driver scan plugin that we saw before, and it just kicks out ones that it thinks are weird. And in every rootkit that we studied as part of this project, every single one fell to driver module. When they tamper with the metadata and so on, you're going to find it. So just to kind of illustrate how this works, this is a rootkit called Dirty Mo. This write-up was like really awesome. Oh, you can see the browser or whatever generates this said it would be almost a 40-minute read. I mean, this company like tore this rootkit apart. So we got a sample, a malware sample, so the driver file. We then created a memory sample out of it. And so you can see us running Volatility 3 against it. The offset, this is the data structure address. But the start that should tell us where that executable is in memory is 0 and the size is 0. Like I said, this is what you're going to see in most cases. So you could, I don't know, run driver scan and grep for 0 and hope you get lucky, but that's not very automated. So instead, you could use driver module. So again, what this does is just prints out drivers that it thinks are weird. Something to be aware of is this known column. So there's like 8 or 9 drivers that will, legitimate drivers on a clean system that will always trigger this plugin. And so what known says is like, yeah, we know this is going to do it. You can ignore it. Obviously, you could configure the plugin just not to print those if that's easier for you. But in this case, it finds the weird dump EDC B5 A3C automatically. And that's the only one it shows that isn't true. It only produces 2 lines. The slide's not cut. So it tells you this one that you can ignore, and this one it's like, hey, something's wrong. And we know that the reason it couldn't map the driver to anywhere is because these are broken. So with just running one plugin, every rootkit that we found, that we studied as part of this, immediately fell to driver module. So that's good and bad, right? Like now you know you have a rootkit on the machine. You don't immediately know where it is in memory. There's some, I'm not going to talk about it here, but there's some more advanced memory forensics techniques you can use to find that in memory. But the idea is, you know, we definitely need to investigate this system further. So besides being able to still tamper with the metadata that they have available, some of the common techniques that rootkits have used forever still work. And it's not just that these are available, the rootkits are still actually abusing them. So the idea with IRPs is if you want to send a request to a kernel driver, so again, I like the NVIDIA example, say you tell your, through that GUI, you tell the NVIDIA driver, hey, I want the fan speed to be 50%. That GUI is going to take that value, it's going to encode it, and obviously it can't talk to the driver directly because the driver's in kernel space. So it's going to use one of the IRP requests that the driver's expecting and say, hey, this is the fan value that the user wants. And this happens for everything that is in a privileged space. Your random notepad that's running can't write directly to the hard drive. Your browser can't write packets directly to the network. You can imagine, so if you think of it as whenever you want to talk to a hardware device or you want to deal with a privileged part of the kernel, those processes have to make a request, because obviously the kernel can say no. If you try to overwrite a file you don't have access to, that gets denied and there's nothing you can do about it. So there's plenty of legitimate reasons why these exist. Operating systems would have no security and no real features if they didn't. But this also gets abused heavily by rootkits, because a rootkit can start, you can imagine you get some type of like connect back to a machine you're running as an unprivileged user. Well, using the software that the rootkit authors write, you run it and you say, hey, I want my process to run as system, or hey, I want my process to be hidden from the live machine, and now sysinternals, task manager, all of those won't be able to see it. So analyzing these IRP handlers is really important because basically every rootkit uses them to talk to back and forth with its processes. These are the entries. Again, this slide isn't cut, so this is a full IRP listing. Read and write we talked about, so if you're trying to write to a file system or read from a file system. From a rootkit perspective, the ones that have in red, these device control calls are how you ask a device to do something and read the response back. So again, I want to hide process 42, or I'm making network connections on a certain IP address, make sure those are hidden from netstat and TCP view and so on. All of that will go through here. We have a plugin to enumerate these handlers in Volatility. It's called Driver IRP. What we're looking at here is a clean system, just so you kind of get the idea. And this is the normal flow. So you have all of the handlers for the different driver. And normally what happens is this last column here is the driver that's handling the request. And this first column is the name of the driver. So you can see for the create call, that's being handled by the NTFS driver. For named pipe, it's being created by NTOS kernel, which is the kernel. And in most cases, this is what you expect. The driver either handles the request itself, or it's a request it doesn't care about, like maybe, so NTFS in this case probably doesn't care about named pipes. It just tells the kernel, hey, I don't care about this one. There's a certain value that can be set, and then the kernel will handle it on behalf of the driver. So it's just a much cleaner way to write the code. As I mentioned, rootkits like to do two things with IRP handlers. One is they have their own, so that their associated processes could talk to them. And then also when they want to take control of a system and hide things, a really good way to do this is to hook the IRP of the driver that's responsible for it. So if you hook, say, the NTFS driver, then you want to hide the presence of your file, or if AV is going to scan that file for signatures, and you just make that file all zeros or all Fs dynamically as it's being read, the AV is not going to find that you're there. So this happens a lot. Again, there's some documentation that PatchGuard, like I put supposedly because again, I've never seen it happen, but for what's deemed critical drivers, which I would only could assume is like the network stack and the file system and so on, PatchGuard's supposed to crash the machine if these are hooked, but I've never seen it happen. And we tried on the latest versions of Windows we could get and such, and I don't know, PatchGuard didn't do anything. So this is looking at driver IRP against Ghost Emperor. This is the same plugin we saw before. So in case you forgot, when we ran driver module, we got it that way. So against Ghost Emperor, this was a rootkit published about from Kaspersky. This was another really, really good write-up that Kaspersky did. So for this one, they said that TCP connections were hidden on the live machine. So again, netstat or TCP viewer or anything else like that. Those were hidden because NSI proxy, so that's the network stack, its in and out control handler was hooked, which is the one we saw before, is what handles requests out to the device. So running driver IRP and volatility, if we focus on NSI proxy, I picked a couple ones that aren't hooked. So you can see the driver's NSI proxy, the handler is NSI proxy, but then you have device control, so that IOCTL handler is dashed because volatility is like, I don't know what this is, it doesn't map to a driver. If you look at the address range here, it's like E38A8 compared to the legitimate ones are F80. And if you look further in the driver IRP output, we have this weird like dump audio codec 0 right in that same range. And that doesn't map to a module either, which is super strange. And this is an example, if you run driver module against the sample with Ghost Emperor, this dump audio codec 0 gets reported right away because it's hidden and it's malicious. So again, inspecting the IRP handlers, especially for things like the file system, the network stack, this, not everyone, but a majority of the rootkits we looked at did something like this. Driver IRP found them right away. The next thing is the device trees. So Windows has this layered architecture. I stole this out of our book. So if it looks familiar from Art of Memory Forensics, that's where it came from. The idea is multiple drivers can register to be involved when operations happen on a device, so the network stack, the file system, and so on. So what rootkits will do is they will attach as the first or the last, depending on what the particular operation is, so they have full control. So again, they want to hide from AV reading from the file system or something reading from the network stack, then they're free to do that. This is Volatility's device tree plugin. This is on a clean sample, just trying to show you that we have your hard disk volume 3, so your C or D drive, whatever it might be. You have all these legitimate components attached to it. You can see the filter manager attached to NTFS. The QoS subsystem attached to the network stack, those are all normal. But what you don't expect, and I've highlighted 2 rootkit reports here, is on this case we're seeing NSI proxy, which is again the network stack, weird kernel module called CRT sys that you don't expect to be there. You don't expect anything besides legitimate components. This matches 100% with the report from this rootkit. It says the rootkit attaches to NSI proxy's device stack. The way that IRP was hooked on a couple slides ago to hide network connections, this achieves the exact same thing without having to hook the IRP handler. And I've seen nothing to where Windows is going to try to stop device attaches for critical devices. So even if the IRP thing gets blocked off, this will still work. This is back to the dump audio codec rootkit we saw before. This is from Kaspersky. They said the NTFS-based driver gets hooked. The rootkit attaches to its stack, and you see that perfectly here. So NTFS, the filter manager that we saw on the previous slide, and then we also have dump audio codec, which driver module would have told us right away was malicious. 2 more things. There's callbacks. So in Windows, kernel drivers can register callbacks for a dozen plus system events. So if they want to know when processes are created, when file systems are registered, when the registry is accessed, when the system's going to shut down, really full control of the system and able to tamper with a wide variety of stuff. So if like an AV process is going to start, they can kill it. If the AV process is going to spawn a thread, they can terminate it. If they want to inject code into a process before it can even run, they can do that. And then the registry's very powerful because they can manipulate the entire registry as the system sees it. So if you use regedit or like PowerShell scripts to try to enumerate things off the machine, any type of auto run tools, if that kernel driver is there, it can hide all of it. Windows 10 plus, so no version of Windows tries to stop these. That seems really difficult. I don't know exactly how that would work anyway. So we want to be able to detect them. This is running the callbacks plugin against a machine infected with a rootkit. You can see that one of the IO registration ones, so when the machine's going to shut down, rootkits will do a couple things as the machine's shutting down. The most common one is to check their persistence. So if they registered a service or they have an auto run key in the registry, they want to make sure it's still there. It's also why you can try to clean machines live and then reboot it and the malware's back because the malware got that last chance to reinstall itself before the machine went away. So we're seeing that here. This callback address is exactly where the rootkit's active if you're going to try to do some type of static analysis. In this case, we were able to find the driver, but not the module. So this is something that driver module would pick up. And then we have a CM register callback, which is how you hook the registry, and that doesn't map to any known driver. So with callbacks, you can really just grep unknown across the plugin, and if something hits, it's going to be a rootkit. And most of the, I don't know if I can say every, but the majority of the rootkits we looked at registered at least one callback. Now, the other thing that's cool, and this is the last artifact I'm going to show, is this technique called get cell routine hijacking. So since tweeting about this at one point, I found out like a Kaspersky researcher commented on it and said that they saw rootkits doing this like apparently like a decade ago and then never saw it again for whatever reason. So I'm still going to call it new because there's the rootkits in the last couple of years are the first time it was really documented online, but it's something to know about anyway. So the idea is these callbacks are extremely powerful, but if you're in the kernel, so like you're an EDR developer, you have your driver in memory, it's actually really easy to find those and enumerate them the same way the plugin does. So at that point, the EDR software can say, hey, this weird driver I don't know has a callback registered. It can try to scrape it out of memory, submit it to its cloud-based whatever. It can run analysis on it. So registering a callback is not stealthy by any means. So what these rootkits that we saw in the last couple of years were doing is what we call get cell routine hijacking. And the idea is they can hijack all the operations in the registry without actually registering a callback for it. So what we're looking at here is this is a memory sample infected with this technique, but we're not seeing it on the slide. This is just to illustrate something. So it's called hive list. We're enumerating all the registry hives as Windows keeps them in memory. Obviously, the registry is consulted all the time, so Windows doesn't go to disk back and forth multiple times a second for it. So it has a cache of all the registry hives and all their stored data in memory. And with Volatility, you can inspect those hives, you can inspect all the keys and data, but the interesting thing is every hive that's listed here is represented by one of these data structures in memory. And even if you're not a programmer, just follow along. The idea is the data structure is called H-hive. So there's one H-hive for each of these lines. So you can see like the software hive, system hive, SAM hive, and so on. And then inside of that data structure, so as part of each of these things, is a get cell routine pointer, which is what's called when you try to do something with that registry hive. We try to enumerate a key, write a key, enumerate a value, and so on. So if you control this call, you control the registry, and you can hide everything you want, just like you can with a callback. So we have a new plugin in Volatility called Get Cell Routine. It from a programmatic standpoint, walks this list. It checks the Get Cell Routine member for every hive. And if the handler for that points to anywhere but the kernel, it reports it. So you can see in this case, the system hive is hooked. It's pointing to a module called CRT-sys. And this module is not hidden. This is one of the few rootkits that driver module wouldn't see right away. But it doesn't matter because it should be in the kernel anyway. This is the handler. You can start your reverse engineering. So the end result of this is we wanted to make sure Volatility and our techniques could find every rootkit technique out there like normal. We had to update some plugins. We had to write some new plugins. We learned a lot along the way, and that was the result of it. I only have a couple minutes left, but before questions, you might have noticed some slides had these numbers in them, like 16, 17, and so on. The last slide, which will be online, is all of those references. So if you want to read about all the rootkits and DSE stuff that came out, you can email me, I can send it to you, or the conference will post it online also. Thank you for attending. Any questions or anything? Yeah, send me an email because, so at Volexity where I work, we actually have a person who spends a significant amount of time making like proof of concept stuff for us to test on also and like modifying them. And I'm not going to call any out, I probably don't remember off the top of my head anyway, but some claim support for like unlinking processes and stuff on Windows 10, which like isn't a thing, like that'll blue screen. So if you shoot me an email, DFIR, you can send it to my company one. I can send you the projects that we have like use as a base to make proof of concepts that I know work on Windows 10. And if you have even like Visual Studio Community, you could get them compiled, and then you would just have to turn on test signing on your machine, and then the driver would load and stuff. So, no problem. Any other questions? There's a light, so I don't see much. Yes.
Some of the samples you have here in memory, is ran against the very voltage against these available anywhere, or is it on our own?
Most of them I get from so some of them are customer samples like that we just changed the addresses and things like that, but a lot of them are on VirusTotal, and so if there's specific ones you're interested in, I can double check and probably get you a copy. You'll want to use OSR Loader is normally how we do it. It's a software tool where you give it a path to a driver, it creates the service, loads it, and all of that, and then you can do it. I have 1 minute left. I'll be around a few minutes after anyway. Say when I have a super quick question. Yes. I can't hear. No, I mean, because we have a bunch of VMs that we use from like early Windows 10 and then some that update all the time, and we test them out on the same ones. The only time it falls apart, which is like Windows basically getting lucky, is sometimes some of these things, operations require like non-documented data structures. So the rootkit's coded like, if I'm running on this version of like subversion release of Windows 10, do this release, and then Windows just gets like old, like newer than the malware supports, so it doesn't work. But theoretically, if that malware was updated with the newer offsets, it would work. So it's not like a protection fix, it's just the malware needs to get updated. So, which is why we do the proof of concept stuff to like our own code to test it. So.
I have one final question for you, Andrew. What is your perspective from a cloud point of view as far as all of this?
Oh, I mean, we often, because it's like boring when we're doing trainings or like even internal stuff to always see like C user Andrew, whatever. So we just spin up like AWS stuff all the time and infect it, take a memory sample, turn the instance down. It doesn't, I mean, it's still Windows or Linux or whatever it is. I've never touched Mac in the cloud, so I'll clarify that, but I've done, yeah, I've used like Windows and Linux. I mean, like whatever the cloud provider is isn't like inspecting your VM to that level to stop maybe if you threw it on like a S3 bucket unencrypted, I don't know, maybe something would get scanned, but like inside the actual instance, no cloud provider changes anything. So.
I think you guys have a conversation at your convenience because I actually do cloud forensics. I teach it at various conferences for the past 6 years.
Okay, yeah, that would be cool. Let me know. I'm going to be around. I have a flight a little later today, but I'll be around. I'm not like running away right after this. So, thank you all again.